This video is about the Net Change Theorem, which allows us to interpret definite integrals in applications. First, we will state the theorem, and we will use the theorem to interpret some definite integrals. And then we'll look at some specific applications that come up relatively often. We'll use the net change theorem to find the displacement of a particle on a time interval from t equals a to t equals b. And we'll also use the net change theorem to find the distance traveled by a particle on the time interval from t equals a to t equals b. And so here's the theorem. It says, if f prime of x is the rate of change of some quantity, f of x, then the definite integral of f prime of x on the interval from x equals a to x equals b yields the net change in f on that interval from a to b. So what we're saying is, I've got the integral from a to b of f prime of x dx. Well, according to the fundamental theorem, the first thing we do if we want to evaluate this this integral is we take the antiderivative. Well, the antiderivative of the derivative is just the original function f. And then we plug in b and we plug in a and we subtract and we get this. So this is really just the fundamental theorem of calculus. We're just looking at it differently. We're thinking of f prime of x as the rate of change of some function. And we're saying if you integrate that rate of change, what you're going to get is the net change in the original function. So this is just the first part of the fundamental theorem. It says if f, little f, is continuous on the interval from a to b, and that capital F prime is equal to lowercase f, so that means that capital F is an antiderivative of lowercase f, then the integral from a to b of little f is equal to that antiderivative evaluated at b and a, and then we subtract. So all we're doing here is saying, well, if f prime and f are the same thing, why don't we just substitute that in, and then why don't we think about it differently? This is the instantaneous rate of change of some function. And this is the net change in the original function. Okay, so let's look at it in a couple of applications. So let's say we're told that r prime of t is the rate of growth of a dog in pounds per year. The first question says, what does r of t represent? Well, r of t is the antiderivative of this derivative. So if this is the rate of growth of a dog in pounds per year, and I undo that operation, so I've got sort of pounds per year here times years, that dt represents some tiny change in years. When I'm done, the result is a number of pounds. This looks like it's going to represent the weight of a dog at a certain time, or the weight of a dog at a certain year. So t must be time in years, and r of t must be the weight. So that's what that would represent. And the reason I'm saying that time is in years is because we've got these units, pounds per year. R of t must be the weight of the dog in pounds. And I think this makes sense given what we know about rates of change. R prime of t can be written this way. I love that Leibniz notation because it reminds me of slope. This tells me I'm looking at instantaneous change in r as time changes. So we're saying, how does the weight change as that number of years changes? So the units for r prime of t are always the units of r divided by the units of t. So when I see pounds per year, some number of pounds per year, that tells me the units for r must be pounds and the units for t must be in years. Okay, so what does r of t represent? It represents the weight of the dog in pounds. Well then, what does this represent? I've got the integral from 2 to 6 of r prime of t dt. And whenever we're asking for interpretations here, don't tell me it's the area under the curve. We know that that represents an area geometrically, but that's not what we're concerned about here. We're talking about a dog and its weight and its rate of change in pounds per year. What does this represent in terms of the dog and its weight? That's what we want to know. So let's write this down. Well, actually, let's draw a picture. So I've got r prime of t over here. And the units for r prime of t are pounds per year. That's on my y-axis, what used to be my y-axis, and this is t, that's time in years. And so if I'm looking at the area under the curve from t equals 2 to t equals 6, that's what we're looking at. We're looking at that area right there. The question becomes, what does that represent? Well, it looks like I'm taking a number of pounds per year, and then I'm multiplying by a number of years. Pounds per year times years should be some number of pounds. Saying like, but what number of pounds? Like, what exactly does it represent? Let's write it out. The integral from 2 to 6 of r prime of t dt. If I wanted to evaluate that, the first thing I would do is take the antiderivative. The antiderivative of the derivative is the original function. Then we'll plug in 2 and 6 and subtract. So what is that? Well, that's going to be the weight of the dog at time t equals 6. So I guess at the beginning of its 6th year. So I guess the way we could think of this is time t equals 0 is when the dog was born, at t equals 1, the dog is 1 year old, t equals 2, that's when the dog turns 2 years old. And then over here, r of 6, that's going to, or r of 6, there's no r shown here, this is r prime. But at r of 6, what that's going to give us is the weight of the dog on its 6th birthday. And then we're subtracting the weight of the dog on its 2nd birthday. So this is the change in the weight of the dog and I've sort of run out of space, so I'll write this over here. It's the change in the weight of the dog from its 2nd birthday to its 6th birthday. Okay, so that's one application problem. We don't even have r of t, but we can interpret this. We know what r prime represents. If this is a growth rate in pounds per year, the integral of that growth rate over that time interval is going to give us this. And this can be interpreted this way. Well, that's the weight at year 6 minus the weight at year 2. So that's saying, well, how much weight did that dog gain between its 2nd birthday and its 6th birthday? So that is the net change in the weight of the dog. Sometimes people say net change in the weight of the dog from its 2nd birthday to its 6th birthday. Now, if we evaluate this, we're going to get some number. Now, this is a net change over that time interval from time that the dog's 2nd birthday to the dog's 6th birthday. That weight, the weight of the dog could have fluctuated. I mean, there may have been a time when the dog got sick and it lost a bunch of weight. There may have been a time when the owner felt like spoiling him and fed him too much, and then they went to the vet, and then the vet put the dog on a diet. You know, who knows what happened in between? But what we know from this is that the net change in the weight of the dog is given by this area under the curve, or the net change in the weight of the dog can be represented by this integral. Okay, so now let's look at another application. We're told that v prime of t is the rate of change of oil in a tank in gallons per hour. I saw this in an application problem related to an oil leak. So the rate of change of oil in a tank would be negative because it's leaking. I'm going to draw it with a positive rate of change, but just going to make v of t positive for our cartoon over here. So this is y equals v prime of t. Okay. And this is rate of change of oil in a tank in gallons per hour. So the units over here are gallons divided by hours. Okay. And then the units over here, that's going to be the units of t. And if this is gallons per hour, t must be measured in the units of the denominator. So that's time in hours. The question says, what does v of t represent? Well, if dv dt, that's the same as v prime of t, remember, is the rate of change of oil in the tank in gallons per hour. T must be measured in hours, volume must be measured in gallons, excuse me. So if I take the antiderivative of this, I must get that v of t plus c, where v of t represents the volume of oil in the tank in gallons at time t, where t is measured in hours. So when I'm doing this, I'm just sort of aligning this variable here with this variable, with that set of units there. And the variable in the denominator goes with those units. Because remember what this is. This is an instantaneous rate of change. This is delta V over delta T, and we're going to let that change in time approach 0. And then we're saying, what happens to that volume at that instant? How is it changing with time at that instant? Well, that's what V prime of T is giving us. So this is change in volume with respect to time in gallons per hour. So V of T must be volume in gallons at time T, and T is measured in hours. Okay, so that's the answer to part A. What does V of T represent? Volume. Volume of oil in the tank at time T, where T is measured in hours. And this part says, what does the integral from 3 to 7 of V prime of T dt represent? I initially forgot my dt. You always need a dt there. Always need that differential for this to make sense. Well, that's going to represent this. Geometrically, I could draw it this way. That's going to be some area under the curve, but I don't want to interpret this as area now. I want to interpret this using my volume, my time in hours, and all of that. Okay. Well, what does this represent? Well, it represents that area, and let's see, what should that area represent? Well, if I'm taking the integral from 3 to 7 of v prime of t, the antiderivative of the derivative is v of t. Then we substitute 7 and 3 and subtract. So we get v of 7 minus v of 3. Okay, well, what is that? Well, that is the volume of oil in the tank at time t equals 7. So it looks like time t equals 0 is right here. And then an hour later, this was our rate of change. And an hour later, that was our rate of change. At time t equals 7, that was the rate of change. So this is the beginning of the 7th hour. So that's the volume of oil in the tank at the beginning of the 7th hour. This is the volume of oil in the tank in gallons at the beginning of the 7th hour from whenever we started measuring it. I mean, we could have started measuring it at any time, right? So we've decided what t equals 0. Here's when we're going to start taking our measurements. 7 hours later, or at the beginning of that 7th hour, this is the volume of oil in the tank at that time. And this is the volume of the oil in the tank at time t equals 3 hours. So that's at the beginning of the 3rd hour. So what does this represent? Well, it's the change in the volume of oil in the tank from the beginning of the 3rd hour to the beginning of the 7th hour. So we say it's the net change. It's the change in the volume of oil in the tank from, let's say, t equals 3 to t equals 7. Just so that we don't have to say from the beginning of the 3rd hour to the beginning of the 7th hour, but that's what that means. Okay, so we've got this theorem now that allows us to interpret integrals differently, interpret them in applications. So it's not just area. It does represent area. It is this area under the curve between t equals 3 and t equals 7, where the curve is given by v prime. And so I'm taking gallons per hour and I'm multiplying by hours to get area. And then it's going to give me some number of gallons. So this is the change in the volume of the oil. Of course, that's going to be in gallons, which are the same units that I get when I multiply the units for y and the units for t. And it's over the time interval that we were given. Okay. Now here's a specific application that comes up pretty often, the displacement of a particle. And we've talked about this before. If S of t represents the position of a particle, maybe it's moving along a single axis, so moving along the x-axis or moving along a straight line. At time t, then the velocity of that particle is given by the derivative of position. And that's because, remember what this represents. This is the instantaneous change in position over change in time. So we're saying, at an instant, how is that position changing with time? And that's given by the derivative of the position function. So if S is measured, let's say it's in feet, just for example, and t is time in seconds, then the units for this would be feet per second, because I'd have change in feet per unit time. That's velocity. And we know acceleration is the derivative of velocity, or the second derivative of position. That's the acceleration of the particle. At time t. So this is a rate of change of a rate of change. So it's notated this way, or you could write it this way. It's change in velocity per unit time. So that's measured in feet per second, or we can call that feet per second squared. So if our acceleration happened to be 3, what that's saying is that at that moment, that velocity is increasing at a rate of 3 feet per second. So whatever the velocity is right now, 1 second from now, it's going to be 3 feet more. And if that acceleration is constant, 1 second after that, it's going to be 3 feet more. And 1 second after that, it's going to be 3 feet more, or 3 feet per second more, excuse me. So that velocity is increasing and keeps getting faster and faster and faster. Every second, it increases by 3 feet per second. So we've got these feet per second. So that's feet per second squared. Okay, so we've got position, we've got velocity, and we've got acceleration. We can use this with the rate or the net change theorem. If you have velocity, that's going to give us displacement if we take its integral. So let's look at that. This gives us displacement of a particle. It's moving along a line. On the interval from t equals a to t equals b. So we've got the integral from a to b of v of t. That's velocity. Well, the integral from a to b of the velocity is the same as the integral from a to b of that instantaneous change in position with respect to time. Well, the antiderivative of the derivative is just the original function. Then we substitute in b and substitute in a and subtract. And so what do we get? Well, this says that the integral of the velocity function, let's say our velocity function looked like this. From time t equals a to t equals b, gives you the change in position from time t equals a to t equals b. Now, it does not tell you the distance traveled, not unless that velocity happened to be positive the whole time or negative the whole time, then it would indicate distance traveled. Let's see, but this is the change in position from time t equals a to time t equals b. Okay, so that's going to give us this displacement of the particle. Change in position is displacement. That's the definition of displacement. Okay, so that's displacement, and let's look at it in an application problem. And then we'll talk about how to find distance traveled. So here we have velocity is given to us. We're told that the velocity of some particle traveling along the x-axis in feet per second is given by this function. Velocity at time t is t cubed minus 8t squared plus 15t. I wrote 12t, 15t on the interval from t equals 0 to t equals 5. So this is velocity. And we're given units. This is feet per second. And we're told that time t is measured in seconds. Okay. let's say somebody asks you to find the displacement of the particle over that time interval. Well, I can use the net change theorem to do that. I'm told t goes from 0 to 5. So the integral from 0 to 5 of the velocity function, that's the same as the integral from 0 to 5 of the derivative of the position function. So that's going to give us the position at time t equals 5 minus the position at time t equals 0. So that's how we can interpret our result. This is the displacement or change in position from time t equals 0 to t equals 5, 0 seconds to 5 seconds. If I actually want to find that value, I have to integrate this function over the time interval. So let's integrate it. All right, well, it's a definite integral. So if I want to find the integral, the first thing I will do is rewrite if necessary. There's no rewrite necessary. So after that, we anti-differentiate. We'll just evaluate this using the fundamental theorem of calculus. So we add 1 to the exponent and divide by the new exponent, bring the constant down, add 1 to the exponent, divide by the new exponent, bring the constant down, add 1 to the exponent and divide by the new exponent, substitute in 0 and 5 and subtract, and we get 1/4 times 5 to the 4th minus 8/3 times 5 cubed plus 15 over 2 times 5 squared minus 0. So we anti-differentiated, and then we evaluate f of 5 and f of 0 and subtract. And then we simplify. So I'll use a calculator for the arithmetic. I've got 5 to the 4th, oops, let's turn it on. 5 to the 4th divided by 4 minus, open parentheses, 8 over 3 times 5 cubed plus, open parentheses, 15 over 2 times 5 squared. And we get 125 over 12, which is that, about 10.42. Approximately 10.42. And the question is, what are those units? One of the questions is that. Well, velocity was in feet per second. So we are taking a number of feet per second and multiplying by seconds. And so we got feet per second times seconds. That would be 10.42 feet. So from time t equals 0 to time t equals 5, that object moved 10.42 feet, just net. Now that doesn't necessarily mean the total distance traveled by the object was 10.42 feet. It could have gone 20 units in this direction and then back, 9.58 units in this direction, and then got a net of 10.42 feet. So we're talking about a particle that's traveling along a straight line. So the straight line might look like this. At time t equals 0, it's at a certain location. And then sometime later, it might go forward. Sometime later, it might go backwards. Every time it goes backwards, we count that velocity as negative. Every time it goes forwards, we count that velocity as positive. So this is not distance traveled. This is just change in position. Yeah, so this is just change in position over that time interval. Okay, so we simplify. And we've got the displacement of the particle over the time interval is 10.42 feet. Okay. Now let's say somebody asked you to find the distance traveled. Well, to find the distance traveled, I can't just use this change in displacement or this change in position, which is displacement. Because if I happen to start over here and end up over here, and that's, let's say 10.42 units, 10.42 feet approximately, from time t equals 0 to t equals 5, I went a net of 10.42 feet. It doesn't necessarily mean I went straight from here to here. I could have gone straight from here to here and then back. I could have gone backward and then forward a little bit, or gone backward and then gone forward past that. And there'd be all this extra distance that I'm traveling as I move back and forth that it would not be accounted for by this displacement. To take that into account, we're going to have to take the absolute value of this. I know that that may not make sense right now. So in order for that to make sense, I think it would be helpful if we graph this function. So I want to graph the function v of t and then see where it crosses the t-axis and just basically see sort of what's going on with this function v of t. So v of t looks like this. It's t cubed minus 8t squared plus 15t. And I can factor that. I see right away that I can factor a t out from all of these terms. They all have a t in common. Then I'm left with t squared minus 8t plus 15. And then this trinomial, that factors pretty nicely. First times first is t squared. And then outer times outer plus inner times inner has to be negative 8t, and last times last must be 15. So I need two numbers that multiply to give me 15 that add to negative 8. Well, to get a positive 15, the numbers have to have the same sign. If they add to negative 8, they better both be negative. A negative times a negative is a positive, and a negative plus a negative would be a negative. So two numbers that multiply to 15 that add to 8 are 3 and 5 will work. So this is our function v of t. It's a cubic polynomial function. So we know the end behavior from pre-calculus. We know the end behavior is this. Since the number in front of the t cubed, that's our leading coefficient, is 1, the end behavior looks like that. So we can draw a rough sketch of this function v of t. We know it crosses the t-axis at t equals 0, at t equals 3, and at t equals 5. Oops, I don't know why I went so far. I started going 5 units out from 3. That's not necessary. I just wanted to go to t equals 5. Okay. And the end behavior looks like that. So we're going to see something like that over here, and something like this over here. And since each of those factors are raised to the first power, that means our zeros are multiplicity 1. So our function's going to cross the axes there. Now I don't actually know how tall this is, and if I wanted to really know what this function looked like, I could plot more points, I could graph it on a graphing calculator. But there are lots of things we could do, but we're just trying to get a general sense of the shape here. So what we've got is maybe something that looks like this. Because of the multiplicity of these zeros, the graph crosses at each of the zeros and it looks like that. Okay, so what does this represent? Got the integral from 0 to 5 of v of t dt. Well, if this is v of t, and v of t is measured in feet per second, and t is time in seconds, this displacement here represents this displacement here, it comes from the net change theorem. We know that when we evaluate this integral, we get this number and it represents displacement because the antiderivative of the derivative is the original function. So we know all of that, but geometrically, that same number represents the net area between the function given by v of t and the t-axis between t equals 0 and t equals 5. So what this number is it's this value over here minus this value. It's that area minus that area. And that area minus that area happens to be 10.42 approximately, or 125 over 12. Now let's think about what they're asking in the second question though. They're saying, find the distance traveled by the particle over the time interval. Well, the distance traveled takes no account for direction. So if we move forward 5 units, and then we move backwards 5 units, if we start and we stop at the same place, let's say, here's 0 and here's 5. So times t equals 0, we're over here. 5 seconds later, we're over here. And then 10 seconds later, we're back here. So we go from here to here, and then we go back. What's our displacement? Our displacement is 0, right? But what was the distance that we traveled? Well, I went 5 units that way and 5 units back. Okay, so the distance doesn't take into account that 5 that I went backwards. It doesn't call it -5, it calls it +5, because we don't care about the sign when we're talking about distance traveled, right? So that's what's necessary here. If I want to find the distance traveled by the particle, every time I'm going backwards, I need to stop counting that as negative. I need to count it as positive. Say to yourself, well, how does that relate to this velocity function? Remember, velocity is change in distance per unit time. And that change in time, we're always assuming is positive. So this is the limit as delta t approaches 0 of delta s over delta t. And we always assume that delta t is positive, even though this limit doesn't assume that, but anyway, that's beside the point. This is positive. So if delta t is always positive, or if we're always thinking of it as positive, well then the sign of v of t is entirely determined by that numerator, by that displacement. So every time I go in a positive direction, so I go from left to right, just by choice, like that's an arbitrary choice of direction. We're calling that the positive direction, and that's fine as long as we're consistent with that after we made the choice. So every time we go from left to right, this will be positive, but every time we go from right back to left, it's going to be negative. So velocity is positive when displacement is positive. Let's write that down. And we've talked about this before in class earlier this semester, but it's relevant here, so we're talking about it again. Velocity is positive when displacement is positive. So you choose a forward direction. You say, that's what I'm going to count as positive from now on. All measurements are relative, but you've made your choice. You said that's forward. Once you've made that choice, every time you move in that direction, velocity and displacement are both positive. Now, anytime you go in the opposite direction, we're going to count velocity as negative. So velocity will be a negative number when that numerator is negative. So velocity is negative when displacement is negative. So now let's look at our curve and think about what's happening again. It's okay, at time t equals 0, the velocity was 0. And then the velocity was increasing for a while, and then at some point, the velocity got to its maximum magnitude. So we got to our maximum speed heading in that positive direction. So we were going this way. And then suddenly we started to slow down. Now the velocity is still positive here, but we're slowing down. If you're saying to yourself, how is that even possible that the velocity can be positive, but it's decreasing, it's negative? Think about pulling up at a stoplight. You're continuing to go in the positive direction. You're continuing to get closer and closer to that stoplight, but you're slowing down as you approach the stoplight. You're continuing to go forward, but you're going in the forward direction slower and slower. So here what we have is we're at rest, then we're speeding up, we get to a maximum speed, and then we start slowing down, but we're still heading in that positive direction. Then right here, that's the moment when we say, pause for a second, and then we start heading in the negative direction. So from here to here, if I want to find the area under the curve, well, that velocity times time, if I draw those little rectangles, all of those are going to be counted as positive. And then that feet per second times a number of seconds is going to give me a number of feet that I traveled in the positive direction. If I want the total distance traveled, I need to count the number of feet that I traveled in the positive direction, and then I need to add the number of feet that I traveled in the negative direction. So I need to find this area, but I can't count it as negative the way that we did up here. Up here, when we evaluated this definite integral, well, we found displacement. That's the total change in distance traveled. We found that. We found that the displacement was 10.42. But if I'm interpreting this geometrically now, so I'm switching my perspective and I've decided I'm going to interpret this geometrically. Say, well, this is the area, the net area between this function and the t-axis from t equals 0 to t equals 5. So it's this area minus this area. This area gives me distance traveled in the positive direction. So that's distance traveled when our displacement was positive. So we're going this way. We've decided that's the positive x-axis, we're going to the right. If I want the distance traveled in the negative direction, I need to find this area. But instead of subtracting that area, I need to add it if I'm going to get the total distance traveled. Just like if I was over here, if I went from 0 to 5 and then 5 back to 0, well, I need to count that distance of 5 units in the forward direction and that distance of 5 units in the backward direction as the same distance. I'm not worried about a sign. And there is no negative sign when you're talking about distance. We just went 5 units that way and 5 units that way, so we want a total of 10 units. But the displacement is 0 because we started and stopped at the same point. Here we were told that our displacement was 10.42, but that doesn't tell us anything about the distance that we traveled. We went so far in the positive direction, and then it looks like we turned around and we went in the opposite direction. But net, we went 10.42 units from where we started. Okay, so the question is, how do you get this to be positive instead of negative? You just take the absolute value. So if I want the distance traveled of my particle over the time interval, this is how we do it. So on the time interval from A to B, the distance traveled is not the integral of velocity, which would give you displacement. It's the integral of the absolute value of velocity. Do you remember what the absolute value of velocity is? That's speed. It's change in distance per unit time instead of change in position per unit time. So it's velocity, but without the sign. We make them all positive. So if I'm taking that curve from up there and I'm taking its absolute value. So I've got this now. It doesn't quite look like my last curve, but you've got the idea. Excuse me, that's velocity. And the integral from 0 to 5, that shaded area, is displacement. Distance traveled comes from taking the absolute value of this. When the function is positive, it stays exactly the same. When the function is negative, we multiply it by positive 1. Or excuse me, multiply it by positive 1. We multiply it by negative 1. So I'm taking all those negative velocities, multiplied them by negative 1, that's the absolute value. So it flips that graph up like this. Now if I look at the area under this blue curve, that's going to give me the distance traveled. It's represented by that area. And the blue curve, if the black curve was velocity, the blue curve is speed, absolute value of velocity. Okay, now in practice, if I want to find distance traveled, I actually have to do something like this. I need to figure out where my velocity function is positive and negative on the interval in question. In this question, our velocity was given to us on the interval from 0 to 5. They asked for displacement and distance traveled on the interval from 0 to 5. And then you need to figure out where that velocity is 0. We already did that by factoring this, and then we graphed it. And then you need to find the distance traveled on each of the intervals defined by those zeros. So I need the distance traveled from 0 to 3 and the distance traveled from 3 to 5. So we're evaluating this. Question is, how do you actually evaluate that in practice? This is how you do it. First, you set v of t equal to 0 and solve for t. Identify any t values on the interval from a to b. So we're finding out where our velocity function is 0. So we had 0, 3, and 5, and 0 and 5 are where we were starting. So it's really just t equals 3. Then you want to evaluate the integral of the velocity function on each of the intervals defined by those t values, those zeros of the velocity function. So we do that, then we integrate from a to t1, and then t1 to t2, t2 to t3, all the way to b. Now, this time I didn't have 3 intervals, I only had 2 intervals because I only had one t value in between where velocity changed signs. But you're just finding the intervals where the velocity is positive all the time or negative all the time. So you integrate over each of those separately. And then you take the absolute values of all of those and then add them together. So let's actually do this for this function. Oops, that's a different problem. It's for later. velocity is t cubed minus 8t squared plus 15t, and we're on the interval from 0 to 5. And we know that the graph roughly looks like this. And just from our picture, I expect the integral from 0 to 3 to be positive and the integral from 3 to 5 to be negative. So this is going to tell me the distance that I traveled in the forward direction. The integral from 3 to 5 is going to tell me the distance I traveled in the negative direction. I'd like to just evaluate those integrals and then we'll check it out. We'll see what we get. So we set this equal to 0, we solve for t, we see that, we draw our picture, and then we integrate over each of those intervals. So let's evaluate the integral from 0 to 3. Now we've already done this, the integration. It's going to be exactly the same antiderivative as it was before, but it's good practice. So we add 1 to the exponent, divide by the new exponent, bring the 8 down. Add 1 to the exponent and divide by the new exponent, bring the 15 down. Add 1 to the exponent and divide by the new exponent. Then you want to substitute in 0 and 3 and subtract. And we get 3 to the 4th over 4 minus 8 over 3 times 3 cubed plus 15 over 2 times 3 squared. And then when we evaluate at t equals 0, we just get 0. Now 3 goes into 3 cubed 3 squared times. So we end up with 81 over 4, excuse me, minus 8 times 9 is 72, plus 15 times 9, what's that? 90 plus 45, 135 over 2. Okay. I'm not going to spend time in calculus class reviewing how to add and subtract fractions. It's an important skill, but it's not the place to learn that. If you need help, you can always ask me. Okay, and we get 63 over 4, which is 15.75 units. If you're saying to yourself, what does that mean? Well, remember how we interpret this. This is the integral of velocity from t equals 0 to t equals 3. So this is s of 3 minus s of 0. Now, I don't know where we started at time t equals 0, but I know that over the time interval from t equals 0 to t equals 3, our displacement was 15.75 units. So we started somewhere. So we're on this axis at some location. I'm going to call that x naught. And then 3 seconds later, we're at x naught plus 15.75. So our displacement is 15.75. We went that way, 15.75 units from wherever we started. That's why this is called the net change theorem. It doesn't tell us that we're located at 15.75, not necessarily, but it tells us that wherever we started, we're 15.75 units down the road from wherever that was. Okay, that's the first part. Now the integral from 3 to 5 is going to be negative. We can tell that because we see the area under the curve is negative. Now if we didn't have the graph, you could just evaluate the integral from 3 to 5. And then you would see, based on the sign, that that was counted in the negative direction. So we had velocity equals 0 at 0, 3, and 5. We integrate from 0 to 3, then we integrate from 3 to 5. And this time, I bet we get a negative answer. We should, if our picture is correct. Antiderivative is exactly the same as it was last time. I'm going to do this a little bit quicker because we just did it. Just using the power rule. Now substitute 3 and 5 and subtract. So you'll have 5 to the 4th over 4 minus 8 over 3 times 5 cubed plus 15 over 2 times 5 squared. And then you want to evaluate all of this at 3 as well. So you have 3 to the 4th over 4 minus 8 over 3 times 3 cubed plus 15 over 2 times 3 squared. And the 3's reduce, and you get that. Okay. Now I'm not going to bother doing the arithmetic by hand. I'm just going to do all of this on my calculator. So I've got 5 to the 4th over 4 minus 8 over 3 times 5 cubed plus 15 over 2 times 5 squared. And that's that first part. And then we're subtracting, open parentheses, all of this. That's 3 to the 4th over 4 minus, it looks like we've got an 8 times 9 there, so it's minus 72, plus 15 over 2 times 3 squared, which is 9, close parentheses for that second set of parentheses right there, hit equals, and we get a negative, it looks like negative 5 1/3. It's not giving us the exact answer, but I think we can all see that that's negative 5 1/3. Or negative 16/3. Okay, so what does that mean? Well, it means, well, we got a negative value. The function was negative the entire time over that interval. And we know that because of our picture, and we were able to draw our picture because of our knowledge of polynomial functions from pre-calculus. If we didn't know what the picture looked like, we could still set this function equal to 0 and find these values, and we would know that the z or the v values may change signs at those 0 points, because it's going to be 0 here and here the whole time. It's got to be positive the whole time, or it's got to be negative the whole time. Because if it goes from positive to negative, it's got to cross, it's got to go through another 0. So if it equals 0 at 0 and 3, it's either on that side or on that side. So you integrate over that interval, you find out from the integration that value is positive, so we know the curve is positive. When this value is negative, and we know that the function is 0 at 0 and 5 and nowhere in between, well, then we know that the function is negative on that interval. So what does that mean? Well, on this time interval, we went backward 5 1/3 units. So you go backward negative 5 1/3 units. And then you say, well, what was your total displacement? Of course, this is not to scale. Displacement, that's what we found in that last integral. It's this value, that 15.75, minus that 16.3. I said 16.3, minus 16 over 3. So we've got 15.75 minus 16 over 3, and we get that 125 over 12, which is approximately 10.46 units, or 42 units. So we go 15.75 units in this direction, we go back 5 1/3 units, and then our total displacement, that's the displacement as we go from here to here. So we went from here to here to here. The displacement is 10.42 units. Now the distance traveled is this distance plus this distance. So if you want distance, you evaluate this integral, you evaluate this integral, but every time you get a negative answer, you have to take its absolute value. So we have the absolute value of the velocity function on the interval from 0 to 5, that's the integral of the speed function, is the integral from 0 to 3 of that velocity function. This happens to be equal to v of t because v of t is positive on that interval. And then we've got the integral from 3 to 5 of the velocity function. And this is the same as finding that integral from 3 to 5. you're getting a negative result and then taking its absolute value. So we've got 15.75 plus the absolute value of negative 5 1/3 or plus 16/3. And so let's, the absolute value of that negative 16/3 is 16/3. Let's add them together. And we get 253 over 12, which is approximately 12.08, and our velocity was in feet per second, so this is feet. We traveled a distance of approximately 21.08 feet. We went 15.75 units this way, and then negative 5 1/3 units this way, and we add those together and you get the whole 21 feet, the 21 feet that we traveled. But net, the displacement was only 10.42, because when we went this way and we went back, we lost all of that distance that we traveled. Okay, so let's do one more example like this, and then we'll call it a video. I want to make sure that you understand this concept so you can do it yourself. This time, now that we've already discussed the idea, I'm going to spend less time in explanation and try to focus more on fluency, so how you would proceed through this method to get the correct answer every time. Okay, so here is our new velocity function. Second example, same concept. That's our velocity, and we're given a time interval. T goes from 1 to 7. And we're asked to find the displacement over the time interval and the total distance the particle travels over the time interval. We'll start with displacement. Displacement's the easy part because of our net change theorem. The integral from 1 to 7 of velocity is the integral from 1 to 7 of the derivative of position. The derivative of, or the antiderivative of the derivative is the original function. So we get the position function back, evaluated at 7 and 1, and we subtract. So this is a change in position from time t equals 7 to time t equals 1. And remember, change in position is the same as displacement. Or I said t equals 7 to t equals 1. It's t equals 1 to t equals 7, sorry. Okay, so that's how far did we travel from t equals 1 unit to t equals 7 units. Or it's not the distance traveled, sorry, it's the displacement, and it's a change in our positions. Well, in order to find that, we just integrate. We take this velocity function, then we add 1 to the exponent and divide by the new exponent. We're taking antiderivatives, so we just use the power rule. We have add 1 to the exponent and divide by the new exponent. Bring the negative 10 down. Add 1 to the exponent and divide by the new exponent. Bring the 27 down. Add 1 to the exponent and divide by the new exponent. Bring the negative 18 down. The antiderivative of a constant is the constant times your variable. Your variable of integration this time is t. So we antidifferentiate. And then we substitute in t equals 1 and t equals 7 and subtract. So we have 7 to the 4th over 4 minus 10 thirds times 7 cubed plus 27 over 2 times 7 squared minus 18 times 7. And then we evaluate all of this at t equals 1. So we've got 1/4 minus 10/3 plus 27 over 2 minus 18. That's going to give us our answer. So let's figure out what that is. 7 to the 4th over 4 minus 10 over 3 times 7 cubed plus 27 over 2 times 7 squared minus 18 times 7. And then we're subtracting this. So I'm subtracting open parentheses 1/4 minus 10/3 plus 27 over 2 minus 18 close parentheses. And we get that, it's a tiny little thing. 3.4 times 10 to the negative 12. My gosh, is that right? I guess so. Provided I entered everything into my calculator correctly. Looks right to me. Oh, I just erased it. 7 to the 4th though. 7 to the 4th over 4 minus 10/3 times 7 cubed plus 27 over 2 times 7 squared, so that's 49, minus 18 times 7. So we get that. And then we're subtracting all of this, subtracting 1/4 minus 10/3 plus 27 over 2 minus 18, close parentheses. Yep, got the same thing. So it's 3.4 times 10 to the negative 12, pretty tiny. Okay, so tiny, tiny displacement. That's f of b minus f of a, and then we subtracted and we simplified. And we got this tiny thing. Okay, now let's say we want to find the distance traveled over that interval. And if this is in feet per second, you have a tiny displacement of this many feet. And I just want to write that out. That's scientific notation for the 10 to the negative 12. That's 11 zeros, guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and a 3, and then a 4. That's how tiny that is. That's the displacement. Went that much of a unit in the direction of that axis with that arbitrarily chosen positive direction. Okay, that's displacement. Let's see what our distance traveled is. Find the distance traveled over the same time interval. Okay, now in order to do this, I'd like to be able to factor this polynomial like I did on the last one, but it's not 100% obvious. I look at that t cubed and that 10t squared. I could take out a t squared from that, then I'd be left with a t minus 10. I could factor something out over here as well. I could factor out a 9, then I'd have a 3t minus 2. But that doesn't seem to help me. There's no factoring by grouping that I can do here. And so what I'm going to use is possible rational roots. Or actually, I'm just going to plug in a value for t. If I plug in t equals 1, I get 1 minus 10 plus 27 minus 18. You notice that I get 28 minus 28, which is 0. Well, if this t equals 1 is a 0 of the polynomial, then that means that t minus 1 is a factor. And it's okay if you don't remember that, but that's going to help us. If t minus 1 is a factor, that means I can factor that out from this. I can take this polynomial and divide out the t minus 1, and I'll be left with a quadratic polynomial that we can factor some other way. We could probably use the quadratic formula if it doesn't factor nicely. So that requires taking this and dividing by t minus 1. So I will have my velocity function. I want to divide it by t minus 1. So I'm going to use synthetic division. Now, when you're using synthetic division, you place the value of t that would make that denominator 0 over here in a little box. And then you list the coefficients of the t's here, but the t's have to be written in descending order. So you have to have the highest power of t first, then the next lowest power, and the next lowest, and so on. So this is already in the right order. I've got a t cubed, t squared, t to the first, t to the 0. If there are any missing terms, you need to add zeros for placeholders for those. If there's no t squared, I'd have to add a 0 t squared in there. But I've got terms of all kinds that I need. So I can just read off the coefficients here. I've got a 1, a -10, a 27, and a -18. And I'm just going to use synthetic division. So we bring the 1 down. Then we multiply these guys together. I get 1, you put that there, and then you add. Then multiply. 1 times -9 is -9, and then you add. Multiply, I get 18, and then you add, and that's 0. Say, hey, that's pretty good. So these are the coefficients of the polynomial that results when you divide this by this. Now, we were dividing something that was cubic, a cubic polynomial, by an expression that involved a t to the first. So after you take a cubic polynomial and you divide out a linear polynomial like this, the power goes down by 1. The power of this polynomial, when you divide out this one, that exponent is going to decrease by that exponent. So when I take a cubic polynomial and I divide by a first degree polynomial, what I'm left with is a quadratic polynomial. So this is the coefficient of t squared. So I've got that. Okay, so v of t is t minus 1, that was one factor, times t squared minus 9t plus 18. And then if this factors, I want to factor it. I'm looking for two numbers that multiply to give me 18 that add to 9. Can you think of any? What about 3 and 6? Will those work? Hope you said yes. If they're both negative, that'll work. -3 plus -6 is -9. -3 times -6 is 18. So this is my v of t in factored form. Okay. And this is a cubic polynomial with a leading coefficient that's positive. So the end behavior is going to look like the end behavior for x cubed. It looks like that on the ends. So at t equals 1, it crosses, and at t equals 3, it crosses. At t equals 6, it crosses. That's because the degrees of each of those zeros, or the multiplicity of each of those zeros is 1. And then it's going to cross over here at -18 because the function was v of t equals t cubed minus 10t squared plus 27t minus 18. So when t is 0, we get -18. So this is not to scale. But we know it looks like this on the ends. So it's going to look like that, and then it's going to have to cross, and then look like that. Oh, now look at that. I mean, my picture's not great. My picture doesn't quite match this. But this looks like the area that, or that displacement that we go, or that distance that we travel in a positive direction, and that distance that we travel in the negative direction, they almost cancel out. They don't quite cancel out because we have a displacement of 3.4 times 10 to the -12. but they get really close to canceling out. So that area is really close to that area, and that's actually slightly more because the displacement is positive, not negative, even though in my picture it looks like the total displacement looks like it might be negative. That area looks larger than that. But that's the idea. This area over here, maybe it looks like this. Yeah, it's a more accurate picture. This area over here and this area over here, they're really close. Maybe it looks like that. But they're not exactly the same, and this one's slightly larger. Okay, so if I want the distance traveled over this interval, I graph my function v of t, knowing what I know about polynomial functions. And then I find the displacement or the distance traveled from time t equals 1 to t equals 3, and then from 1 to 6. Ooh, and actually they said t equals 1 to 7. Okay, so it's not quite like this. It's this. We're taking that area plus that area, and that almost exactly balances this area. But this area total is slightly more than this area, so we get that displacement of 0.00000000000034. Okay, so I'm going to have to evaluate 3 integrals because I'm interested in the distance traveled on the interval from 1 to 7. So I'll have an integral from 1 to 3. It's going to give me a positive number. Then an integral from 3 to 6. It's going to give me a negative number. I'll take its absolute value to get distance. And then 6 to 7, it'll be positive again. And then I'll take that positive number plus that positive number and the absolute value of that negative number that we get from that integral, add them together, it's going to give me distance. Okay, that's the plan. Let's do it. Okay, so I've got the integral from 1 to 3 of v of t. I want that. Then I want the integral from 3 to 6 of v of t. It's going to be a negative number. I want that. And then I want the integral from 6 to 7 of v of t. And then we're going to take the absolute value of all the answers and add them together. Okay, now v of t was this function. We've actually already taken the antiderivative. It's right there. So we got t to the 4th over 4 minus 10/3 t cubed plus 27 over 2 t squared minus 18t. It's going to be the same antiderivative for all of them. We're just evaluating over different intervals, excuse me. I'm evaluating from 1 to 3 here, then 3 to 6 here, and then 6 to 7 there. And it's the same antiderivative, so I'll just write this down 3 times. Okay. All right, when we plug in 3, let's see what we get. We have 3 to the 4th over 4 minus 10 over 3 times 3 cubed plus 27 over 2 times 3 squared minus 18 times 3. And then we evaluate this at 1. So we get 1/4 minus 10/3 plus 27 over 2 minus 18. We're going to get a number. Figure out what that number is in just a second. And then at time t equals 6, we're going to substitute in here. We'll have 6 to the 4th over 4 minus 10/3 times 6 cubed plus 27 over 2 times 6 cubed. That can't be right. 6 squared. minus 18 times 6, minus the answer that we got over here for the 3s. So I'm going to write that down. We're using it a couple times. And then over here, we're going to evaluate at 7 and evaluate at 6 and subtract. So 7 cubed, 7 squared. I know it's a little tedious. It's good though, it's good practice. Okay. Now let's see what that function is evaluated at 3. So I'll have 3 to the 4th minus 10 over 3 times 3 cubed, so that's 27, plus 27 over 2 times 3 squared, which is 9, minus 18 times 3. So we get 117 over 2. That's this value. And this is also 117 over 2. Just going to keep track of that, okay? And then at t equals 1, we've got 1/4 minus 10/3 plus 27 over 2 minus 18. And we get negative 91 over 12. I actually don't need to keep track of that. But that's what I have there. This is negative 91 over 12. So we have 117 over 2 minus this number. So I'm taking that number, multiplying by negative 1, and then adding 117 over 2. And that gives me the displacement over that first interval. And since it's positive and the function is positive the whole time, because remember what our function looked like, that's actually the distance traveled from t equals 1 to t equals 3. So we get that for our distance, and let's approximate it. It's about 66.08. If this is in feet per second, this is 66.08 feet. So we were going in the positive direction, and we went 66.08 feet approximately. Then at this point, t equals 3, we turned around and started going in the negative direction. If we want to find the distance that we traveled in the negative direction, we need to evaluate this integral and then take its absolute value. So I've got that expression involving 6. So let's figure out what that is. We've got 6 to the 4th over 4 minus 10, oops, let's use parentheses there, 10 over 3 times 6 cubed plus 27 over 2 times 6 squared, which is 36, minus 18 times 6, and we get negative 18. Okay. So that's negative 18, and we're going to use that over here as well. That's also negative 18. So I have negative 18 minus 117 over 2. And we get a total of, for this integral, it's negative 153 over 2, which is negative 76.5. What does that mean? We look at this area over here, that's 76.5 feet. That's the area. But over here, we were going 66.8 feet in the positive direction. Then we went 75 or 76.5 feet in the negative direction. So at this point, after going 66 feet this way and 75 feet this way, our displacement was negative. We're actually a little bit behind from wherever we started. But then we add this little distance, and I think that's what gets us to this 3.4 times 10 to the negative 12, which is really small, but it's not 0. Okay, so let's figure out what this is. I've got 7 to the 4th over 4. I'm subtracting 10 over 3 times 7 cubed. And I'm adding 27 over 2 times 7 squared minus 18 times 7. And I get whatever that number is. I wonder what that decimal equivalent is. That's -5 or -7.583 repeating, it looks like. And we're subtracting a -18 from that. So we're adding 18 to that. And we get 125 over 12. So this is 10.416. Okay, so we went 66 units in the positive direction. Then we went back 76.5 units. So that's like basically -10 units approximately. Then we go forward 10 more units. And then because of that 0.5 and that 0.416 repeating and that 0.08, we end up with this tiny, tiny decimal. Okay, so that is how you evaluate that. You find the total distance traveled on all of those intervals, and those intervals are determined by the t-values that cause your velocity to be 0, because that's where your velocity changes from positive to negative. And if velocity is changing from positive to negative, that means displacement is changing from positive to negative. So this means we're going forward, this means we're going backwards, then we're going forward, and then we take the absolute values of all of our answers. Really, it's just this one, the one that's negative, where your displacement was in a negative direction. And then you add all three of these numbers together. So the total distance traveled, distance is equal to the integral from 1 to 3 of v of t plus the integral from 3 to 6 of v of t, but we take its absolute value because that distance traveled was traveled in the negative direction. And then we have the integral from 6 to 7 of v of t. Now, all of these are technically absolute values of v of t, but v of t is positive here and here. So we get a positive answer, a positive answer. And this one, where we get a negative answer, we take its absolute value. So we've got 793 over 12 minus or plus the absolute value of 76.5, and then we have plus this 10.416 repeating. And so let's see if we get the same answer as we got before. Or actually, let's not take the absolute value yet. We have 793 over 12 that's in the forward direction, minus 76.5, that's how we went backwards, plus that 10.416. Ooh, I'm not getting exactly the same answer, but I think it's because I had to approximate something here. Okay, now I add all of these together, 793 over 12, plus 76.5, plus 10.416. And we get that. That's the total distance traveled. So yeah, it's close. Should be exactly equivalent, but maybe I made a mistake somewhere, or perhaps it was just a calculator rounding error. But this minus this plus this gives me displacement, because we went this way, we went 66 units this way, 76.5 this way, 10.416 this way. We did that. Or if I want distance traveled, I need to count that 66 and then add that 76.5 and then add that 10.6. This plus this plus this is this answer, the distance traveled, which is approximately 152.999 feet. So we want 152.999 feet, but our displacement was almost nothing. So something to keep in mind.